In this video, we are going to cover the LeChatelier Principle, and that would be the kind of the last video for this unit. There's going to be a very last one that's going to wrap in together kinetics and equilibrium while talking about the Haber reaction for the synthesis of ammonia. First of all, let's start with the video. So you have the link for the YouTube video, and when you're done with that, you can come back to this PowerPoint. So as you've seen in the video, the Chatelier Principle tells you that one of the possible statements is that a system at equilibrium responds to a stress in such a way that it relieves that stress. That's a bit cryptic, right? Because what is this stress? So if you remember the analogy with the coins, the very last thing we did was we started from a system that was already in equilibrium because I had in the product flask twice as many coins as I had in the reagent flask. So there was already a ratio of 2 to 1. So when we were going to calculate the movement of coins from one side to the other, we end up with the very same amount for both directions. That means that the even at the very first step, the number of the coins was not changing, and that was because we was already at equilibrium, and Q was in fact equal to K. The K for that particular situation was 2. And then I said, well, what if I reach with my hand inside the flask and I take away half of the coins from the product side? So that would be the stress. So the stress would be any intervention from the outside that kind of alter the status quo, the situation, the steady state. So it could be, for example, removing products or adding products, or removing reagents or adding reagents, or it could be changing the temperature, or it could be changing the pressure. So whatever is altering the equilibrium, we call that stress. So the fact that the system responds to relieve the stress, it's kind of a weird way of phrasing it because it almost sounds like the system has a sort of a free will and can do things. But what does it mean is the change in the reaction, in the relative rate of the reaction, is aimed to bring again the system into a state of equilibrium. And so, for example, in the case of the coins, right, we started from equilibrium, twice as many coins on the product side. I took away, so I reduced the amount of coins on the product side. So when I go to calculate Q, that's number of coins on the product side divided number of coins on the reactant side. Now Q is not 2 anymore, it's smaller. In that specific case, it was becoming 1. So if Q is too small, the rate that's bringing for the direct reaction is going to increase. It's not going to be increased, but it's going to be larger than the one for the reverse reaction. So that is causing a net accumulation of coins on the product side. So basically the effect, so the cause is me taking away the coins from one side, and the effect is more coins moving to that very same side. So kind of nullifying what I did originally. So that's what it means, that the system reacts in a way that relieves the stress. So it's basically a mechanism of negative feedback, as you probably will see at some point in your study of engineering. So there is a set point, and that the K value of K. And whenever the situation is different from the set point, there is a response in order to bring once again the system to the set point. So the set point is going to be the correspondent of our K equilibrium. The disturbance is going to be the stress, basically. And this is also what happens in a lot of biological systems, what is called homeostasis. Like, for example, your body is designed, there are several systems that control the temperature of your body. So whenever the temperature is different from a set value, that's 37 Celsius, there's going to be a response of the system, your body, to kind of relieve the stress. So if the stress consists in you being too hot, the temperature is too high, the system, your body, is trying to do something to relieve the stress, so to bring down the temperature again. So for example, you would be sweating, because sweating through evaporation, so the latent heat of the evaporation is going to cool down your body. If you're too cold, then that's the stress. The value of the temperature is too low respect to the set point, so your body is going to react, for example, by shivering, because shivering is muscular activity and that produces heat, so your temperature can go up again. So it's very much like another example that we can use to understand what's going on is the thermostat in your house. You set your thermostat to a certain temperature. The thermostat in that picture is set for 70. That, for my taste, is a little bit too warm. Mine is set to 65. So if you open the window and heat is going out, it's not, as you know, we kind of learn in thermodynamics that is not the cold coming in, it's the heat going out. So there's going to be a loss of heat, and the system will respond by activating the furnace to, so it is always, the response is always opposite to the change, to the disturbance. As opposed to, let's say, if you open up, let's say you're starting a fire in the fireplace, then the temperature goes up, then the system will respond by shutting off the furnace. Now, there is only one set value for the temperature in your house, in your thermostat. In the example before, it was 70 Fahrenheit. 70 Celsius would be really hot. 70 Fahrenheit. But there are infinite value of temperature that at any point in time your house might have, right? So your house might be too cold, so it may be 55, 56, 57, or your house may be too warm, 80, 85. That's Q. Q can have any value. The temperature in the room can have any value. K is the value you set on the thermostat. So there is only one value for that. Okay. So let's analyze the first type of stress. One type of stress is to alter the concentration. Now, there are products, there are reagents. We can alter both. We can alter them by raising them. We can alter them by lowering them. So let's see, for example, in this reaction, and let's focus on CO2. That's one of the products. If we remove the CO2, Q is not going to be equal to K anymore. So, you know, we always start by a situation where there is equilibrium. At equilibrium, Q and K are equal. If we subtract CO2, we are going to lower this number in this multiplication. So the whole, when you calculate Q and you use the very same formula, the value of Q is going to be smaller. In order for Q to go up, the system will have to respond by shifting towards the products. So the direct reaction is going to prevail. So you can make more CO2 in H2, therefore increasing the numerator, making the denominator smaller. So Q will start raising until it reaches once again K. If you have an heterogeneous equilibrium, you need to be careful analyzing the effect of stress, because only changes in concentration of those species that do appear in the equilibrium constant will have an effect. If you have an heterogeneous equilibrium, certain things will not be written in the equilibrium constant. So, for example, in this case, all species are gas except carbon, that is a solid. So that means that when you write the equilibrium constant, carbon is not there. If it's not there, it doesn't affect K, and then it doesn't affect Q. So no matter what value, how much carbon, solid graphite, for example, you have in that reaction, that is not going to change the value of Q, because the value of Q is going to be calculated with the very same equation you're using for the equilibrium constant. So that means that it doesn't matter if you have a lot of graphite or if you have a very small amount of graphite, it's not going to have any effect on the equilibrium. And the reason is that the carbon is in a different phase. So you have a solution of gases on top, so you have a gas solution. That's an homogeneous mixture of water vapor, hydrogen, and CO. And then in a separate phase, you have the carbon that's solid. So the concentration of carbon is the concentration of carbon in itself, not in the gas mixture, because it's not there. and therefore is always going to be 100%. As long as you have at least a bit of graphite, it's going to have the same effect that having a ton of graphite from the perspective of. Let's have a look at the effect of changing pressure or volume. Why are we talking of those two variables together? Because one affects the other. Because if you remember from the gas law, one of the gas law is the Boyle's law that tells you that pressure and volume are inversely proportional. So for example, if you have this container here with a mixture of gases, you see there are some molecule of gas here represented as little blue dots, and the other one are gray. If you are, and this is the initial volume, so you are increasing the pressure by compressing the gas. So if you're doubling the pressure, according to the Boyle's law, the volume is going to be half. So that means that the concentration is going to double. The concentration of everything, products and reactants. Now, the actual effect of such a change on the equilibrium on the system is going to depend on the stoichiometry, because the system will respond trying to counteract, right? So the same way the thermostat, when the temperature goes up and it is too warm, the system is responding by making the room colder by turning off the furnace. So if we are increasing the pressure, the system will respond trying to decrease the pressure. To decrease the pressure is going to favor, between the direct and the reverse reaction, the one that has the fewer number of gas moles. So if we increase the pressure, the equilibrium moves to decrease the pressure again, so it would favor the side with fewer molecules that are in the gas state. If you have the same number of molecules that sometimes happen on each side, that means that the change of pressure will make no difference. So let's see this example. This is the Haber reaction for the synthesis of ammonia. So on this side, we have a total of 4 molecules of gas, 1 nitrogen and 3 hydrogen. On this side, we have two molecules of gas because we have only the ammonia. So between the two sides, the products has less moles of gas. Therefore, if I increase the pressure, the system will respond shifting towards the products. The rate of the direct reaction will go up, and the rate of the reverse reaction would go down. That means I will make more ammonia. So if I'm in the business of making and selling ammonia, I want this reaction to happen at a high pressure so that I can increase the amount of reactants. If we decrease the pressure by expanding, then we would favor the reagent, nitrogen and hydrogen, because on that side there are 4 moles, so we expand, we increase the volume, the pressure drops, we favor the reverse reaction, we have 4 moles instead of 2, and the pressure goes up again. So let's see 3 examples. Okay, so basically what you have to do in this for this question, you need to focus on everything that's labeled as gas. So this is a simple example because everything is a gas on all sides, right? So you have gas. So these are all homogeneous equilibrium. So what you do, you start counting. So you have on this side, you have 2 molecules. On this side, you have 2 molecules. So this is one of the situations where the number of molecules of gas is the same for reagents and products. So for this first reaction, an increase or a decrease of pressure will have no effect. The second reaction is the ammonia, the one we have seen already. So on this side, we have 4 mole of gas. On this side, we have 2. So if we increase the pressure, the reaction is going, so if the pressure is going up, that is what is asking us, the reaction will favor the side with less moles. While for the example seen above, there was no effect. For the reaction at the bottom, we have 2 moles on this side and 3 moles on this side. So an increase in pressure will favor this side of the reaction because there are less moles. So we've seen the effect of changing the pressure by compressing or expanding the container where the reactants and the products are, and the effect depends on the relative number of moles between products and reactants. But there's another way we can change the pressure of the system, and this is by adding a gas that is not a reactant nor a product. So it's called an inert gas. So in this example, there will be those yellow dots that you can see in the B part of the diagram. So this is an inert gas. So practically, if we consider, for example, the reaction between nitrogen and hydrogen to produce ammonia, the inert gas could be, let's say, due to the addition of argon. Argon is a noble gas with very limited reactivity, almost nothing. Is not a reagent, is not a product, so it's just a filler basically, right? So you can think in terms of collision theory, right? So if we have an extra molecule of gas, there are going to be more collision, but those collisions are going to be between argon and ammonia, or between argon and hydrogen, or between argon and nitrogen, and those are not useful in any way to any reaction. The probability that nitrogen and hydrogen collide together are going to be the same because their absolute amount has not changed. In a more quantitative approach to understand why the inert gas does nothing, consider the equilibrium constant for this reaction in terms of concentration, molar concentration. The concentration of the ammonia depends on how many moles of ammonia you have, and that has not changed. So the number of green dots in A and B is going to be exactly the same. And then the concentration is the number of moles divided at the volume in liters. So we haven't changed the volume, the size of the container is the same, so that has not changed either. So the number I'm going to write here is going to be exactly the same with or without argon. If we express the equilibrium constant in terms of partial pressure, we arrive to the very same result. So in a nutshell, adding an inert gas has no effect on the equilibrium composition. The word inert means that it does nothing. So for once, it's an easy thing to remember. The big assumption is that we have not changed the volume. Obviously, if the volume would change, because I could add a gas, the pressure inside is going to go up. If I keep the pressure constant and I add an inert gas, it's going to expand. But if the volume is kept constant, for example, the container is a rigid container, then adding an inert gas has no effect. And that's a question that it's a tricky one, so they sometimes it pops up in final and quizzes just because they want to see if you get tricked. Okay, in general, introducing something that does not appear in the equilibrium constant because it's not a reactant, it's not a product, does nothing to the equilibrium. So a catalyst is not a product, is not a reactant, is not affecting the equilibrium. It's just affecting how fast you get to the equilibrium. Let's see the effects of temperature on equilibrium. The effect of temperature can still be explained in terms of the Chatelier principle, although things are a little bit more complicated than that. So let's start by explaining it using the LeChatelier, and then let's see why there are some issues with this explanation. So let's take once again the reaction of ammonia, the production of ammonia through the Haber reaction. This reaction happens to be exothermic, and the delta H of the reaction is negative. So as you have seen in the thermochemistry unit, we can write the heat exchange as either a product or a reactant, depending if the reaction is exothermic or endothermic. Because in an exothermic reaction, the heat is given off, we can write it as a product. So we could write something like that. So we already know what's going to happen if, let's say, we increase the amount of ammonia, right? If we manipulate the concentration of the products, so if we add more products, what's going to happen is that the Q is going to become too big, and so we will shift the equilibrium towards the left in order to counterbalance what happened and bring down back the concentration of ammonia. So we can reason the same way with the heat. If the heat is increased, that means if we're making the system, we are increasing the temperature of the system, the system gets more hot, the system will react in the same way as it reacted for an increase in ammonia. We will shift the equilibrium towards the left. Now, this is going to be the opposite, obviously, if the reaction is endothermic. If the reaction is endothermic, we would write the heat as a reactant. So to increase the temperature will be the same as to increase the reactant. Now, why is it that, although this explanation works, so in terms of answering question, you're just going to be fine. If one wants to be rigorous, it's not really, it's a little bit more complicated than the other thing, because every other thing we have considered, changing the concentration of the reactants or changing the concentration of the products, changing the pressure, changing the volume, all those manipulations were not changing the value of the equilibrium constant. But the temperature does change the equilibrium constant. So when we heat up the system, or we will cool down the system, we are actually changing the value of the K. And so that makes things a little bit more complicated. There is, in fact, an equation that we will see at the very end that states the mathematical relationship between delta H and equilibrium constant. There are several reactions where the difference in color between the hydrogen product make it more obvious to see the effect of temperature on equilibrium. So in one of the movies, in one of the videos that I give you the link for, the reaction they were using was N2O4 decomposing into NO2. But another example is this one with cobalt complex ions that you would have done in the lab, except we shifted to online teaching. So these are compounds that have pretty complicated looking formulas. So you have an ion that's a transition metal, in this case is cobalt, and then it's bonded covalently to water or other molecule. And these molecules that are bonded to the positive ion are called ligands. So this is not like water in the sense that the cobalt is dissolved in water. This is water that's actually bonded in a very specific number, in a very specific way, in a very specific ratio to the cobalt, so that you can actually write a formula. And so they're called ions because, as you can see, there is a charge, and they're called complex ion because they are complicated, right? So the thing is, you can swap water with chloride, as you can see in this reaction, and the two compounds have very different colors, and the reaction is an equilibrium. So if you have mostly, the cobalt is mostly bonded to the water, is pink, and if it's mostly bonded to the chloride ions, is blue. And the color is affected by the temperature. So if you are warming up, you see shift towards the blue coloration, while if you're cooling down, you see a shift towards the pink coloration. And I'm using blue and red like the coding of the faucet, right? So what does that tell us? So we can actually infer if the reaction is exothermic or endothermic, and that would have been a question in the lab report for this unit. So if an increase in temperature favors the blue compounds, that means that increase in the temperature, it has the same effect as increasing the reactant, right? So if I would increase, I'm trying to get the pointer here. If I would increase the reactant, I would see a shift in this direction. If I increase the heat, I see the same effect. This tells me that heat has to be one of the reactants. So heat is written on the reactant side. That means that the reaction is endothermic. Finally, there are a couple of tables that kind of summarize everything, and I put two because I like different things between the two tables. I like this table because it kind of clarify what do we mean with stress and what do we mean with shift. So basically, the stress is the cause of the change, the trigger, and the shift is the effect. And then you have an explanation of why things happen. I like it also because it includes the fact that the catalyst has no effect on the reaction. The second table, it's calling things different. So you see change, and that would be the stress, and you see the effect, that would be the shift, right? And what I like about this is that it gives you, it reminds you what is actually changing the value of the equilibrium constant and what is not. And so the very important thing is that the temperature is the one that's changing the equilibrium constant. The way in which it changes the equilibrium constant, so does it make it bigger or does it make it smaller, depends on the value, on the sign. So in terms of equilibrium, the catalyst does not change the equilibrium. The catalyst does not change the delta H of the reaction, and that's the factor that would have an effect on the equilibrium constant, but the delta H is going to stay the same. It just provided a different path. In this case, you see that the uncatalyzed path has only one bump, so it's just one step in the mechanism, while with the catalyst you have two steps. And you have a lower activation energy. That means that the direct reaction is going to be faster, but also the reverse reaction is going to be faster. So they're going both to be faster. Their ratio is not changing, and that means that the value of the K is not changing. You might remember when we talked about liquid state and evaporation, and we talked about the Clausius-Clapeyron equation that relates the vapor pressure to the temperature. The evaporation is an equilibrium between the liquid phase and the vapor phase. So it is no surprise that a very, very similar equation is the equation that connects the equilibrium constant to the delta H of reaction. And that's called the Van 't Hoff equation. So you see that you have, let me get the pointer here. You have the logarithm, so it's expressed as in the logarithmic form and then as a ratio, right? So that's the K2 and K1 are the two equilibrium constants at the two different temperatures. K2 is the equilibrium constant at the higher temperature T2, and K1 is the equilibrium constant at the lower temperature T1, temperature that I measure in Kelvin. R is the gas constant expressed as usual in joules, and you have a minus sign, and then you have the delta H of reaction. So you can see that depending on the rate on the sign on delta H, so if the reaction is exothermic, this is going to be negative. If this is going to be negative, with the minus that you have here becomes positive, right? So the sign then depends on this subtraction, because T2 is at higher temperature. T2 minus T1, the reciprocal of T2 minus the reciprocal of T1 is going to be negative. So that means that this logarithm is going to be negative. That means that K2 is going to be smaller than K1. So for an exothermic reaction, we are going to have that an increase in temperature is going to decrease the value of the equilibrium constant. So you're going to get less product. That makes sense because heat would be product. Now, there are these three equations that really look very similar. One is the Van 't Hoff equation, one is the Clausius-Clapeyron, and then this one is the Arrhenius equation. Now, the good news is I'm not going to give you calculation with the Van 't Hoff equation. If anything, I may ask you to predict, to do some reasoning in terms of, if T2 is the higher temperature, T1 is the lower temperature, delta H is negative because the reaction is exothermic, what do you expect to be the effect of the relative ratio of K2 and K1? So that would be the only question that I would ask you about that. So as you might remember, there are two ways we can express the equilibrium constant if all the species involved in the reaction are gas. So we have a homogeneous equilibrium that is in the gas phase. One is to use molar concentration, one is to use partial pressure. The two numbers you would come up with are different. There is a relationship that connects the two numbers. So allows you to convert from Kp to Kc and vice versa. So this equation has the value of the Kp, the value of the Kc, then you have R, that is the gas constant, this times in liters per mole, because this equivalence is calculated using the gas law, the ideal gas law. T is the temperature in Kelvin, R is the 0.082, delta N is the number of moles of C, so that would be the small c, plus the number of moles of D in the balance equation, so you go C plus D minus B minus A. The reason you have this equation is the equation can be derived by using the gas law, solving for P, and so you will get that P is equal N divided V, where N is the number of moles, V is the volume in liters, so this ratio is nothing else but the molarity. And so you can substitute in the Kp those values, and if you move close to each other the molar concentration, you see that that looks very much like the Kc, and then you can just put together RT elevated to C plus D plus A per B. Now, do you have to know how to prove that equation? No. That equation that converts Kc and Kp is given in the cover of the exam. So all you have to do is use that equation to do the calculation. Okay, so again, just to be clear, this equation is given in the test. So you need to remember what delta N is. It's C plus D minus A minus B, where these are the coefficients in the balance equation. And for R, you need to use this value because it's coming out of the gas law. So